In the first part of 2.1, we talked about finding the derivative of a function by using the limit definition of a derivative. What we're going to do in this section is we're going to extend that idea of finding a derivative to the idea of whether or not a function is differentiable, or whether or not we can find a derivative at every value of a particular point. We're going to talk about why in certain cases we can't find the derivative, and then we're going to talk about how to find the derivative at a particular point using the alternate definition of a derivative. So, differentiation is a term for finding the derivative. It's the verb. We talked about what the derivative was in the last video. Now we're saying if we can take the process of finding the derivative is differentiation. A function is differentiable at a particular value if the derivative exists at that particular value. Or we could say it's differentiable everywhere if the derivative exists everywhere. Another way that we can think about the definition of the derivative is if we want it at a particular point, we don't need to go through that whole limit as h approaches 0 of x plus h, f of x plus h minus f of x over h. If we're looking for it at a particular value, why not take the limit as x approaches that value, and instead of having f of x plus h and f of x, just actually use that value. So this right here is the alternate definition for the derivative at a particular point. So we can't use this to find the derivative as a function like we could in the last video. We can only use this to find the derivative at a particular c value. Another thing that we can add in, now that we've talked about left and right limits and now that we've talked about derivatives, is that a derivative is going to exist at a value if the left side of that derivative is equal to the right side of that derivative. If we take the derivative from the left and the right and we get the same value, then the derivative will exist. It also has to be continuous. In order for a function to be differentiable, it must be continuous. So only continuous functions can have derivatives, or it can only have a derivative over the values in which it is continuous. So what are some reasons that a function may not have a derivative at a particular value? Well, it might not be continuous. We've talked about having a vertical asymptote, having a hole, or having a jump discontinuity, or an oscillation. So all of these are types of discontinuities. If a function is not continuous, then it can't be differentiable. So if there is a discontinuity at a particular value, then we can say that the derivative doesn't exist at that particular value. A sharp turn, meaning what's happening from the left and what's happening from the right are not going to be the same exact value. That would also be a reason where the derivative wouldn't exist. And that happens with absolute value curves at the vertex of the absolute value curve. It also happens in piecewise functions when we can look at what's happening from the left and the right and it's not behaving in the same way. And lastly, the derivative doesn't exist when there is a vertical tangent. So when our graph, the tangent line would be a vertical line. The reason being there, our derivative would look something like 1 over 0 if we were actually calculating it by hand. That would be the sign that the slope is undefined, so the tangent line would be vertical. So these are the three reasons that a function may not have a derivative at a particular value: a discontinuity, a sharp turn, and a vertical tangent. Now, if you look at examples A through E down here, each of these graphs has an issue at the value x equals 1. So I encourage you to pause the video and see which of these three issues or which of these three reasons is causing it not to be differentiable at x equals 1. Okay, hopefully you've had time to pause the video. For part A, we have a discontinuity. Since we have a hole, that's why it's not differentiable at x equals 1. At part B, we have another discontinuity. We have a jump. That's why B would not be differentiable at x equals 1. For C, we have another discontinuity. We have a vertical asymptote. That's why at x equals 1, the graph in C would not be differentiable. D has a sharp turn at x equals 1. That's why it would not be differentiable. And then for E, we have a vertical tangent line. That's why it wouldn't be differentiable at x equals 1. So you're hopefully getting some visuals of the reasons why, from looking at a graph, a function might not be differentiable at a particular value. What we're going to spend the rest of this video doing is working with this alternate definition of the derivative to find the derivative at a particular point. So for each of these 4 examples, it says use the alternate form of the limit definition for derivative to find the derivative at x equals c. So each problem is giving us a specific c value. So we are going to take the limit as x approaches c. In this case, that's 1. So as x approaches 1 of f of x, I'm going to write it out, times f of 1 over x minus 1. I'm not going to write this first step on every problem, but on this I want you to see where everything is coming from. So the limit as x approaches 1, f of x is x squared minus x. F of 1 is what I get when I plug 1 into this function. Well, that's going to be 1 minus 1, which is going to be 0, over x minus 1. Now we have a limit that we have to evaluate. So I can't plug in 1 right away. I get indeterminate form, so I'm going to try to factor. This does have a factor that divides out, and then if I plug 1 in there, I just get 1. That means, and I'm going to come back up here, f prime of 1 equals this limit, so f prime of 1 is equal to 1. So again, we're not getting the derivative as a function here, we're getting the derivative at the particular value that we're looking for. So let's walk through this process again. We're going to say that f prime of 1 equals the limit as x approaches 1. X is approaching 1 because that's the value that we're trying to find the derivative at, of f of x, which is x squared plus 2x, minus f of 1. If I plug 1 in here, 1 squared plus 2 times 1 is going to be 3. And this is all over x minus 1. Now I need to factor so that I can evaluate this limit. So this is going to factor to x plus 3, x minus 1 over x minus 1. That's going to divide out. And now I can use direct substitution to get 4. So f prime of 1 equals 4. The derivative of the function x squared plus 2x, when I evaluate it at 1, is equal to 4. I encourage you to pause the video and try and work through number 3 and 4 on your own, and then unpause the video and see how you did. So here's the setup. I would rather not look at this complex fraction, so I'm going to write my denominator as a fraction, 1 over x minus 3. And then I know I'm going to need to find a common denominator. So here I'm going to need to multiply this by 3 over 3 and this by x over x. So that's going to give me 3 over 3x minus x over 3x. And now that I have a common denominator, I can combine this to just be one fraction, 1 over x minus 3 times 3 minus x over 3x. Well, I'm actually going to rewrite 3 minus x is the same thing as negative x minus 3. If I change the sign, so I'm actually going to rewrite this as negative x minus 3 so that I now have this factor that's going to divide out. That's going to give me the limit as x approaches 3 of the only thing that's left in the numerator is negative 1 over 3x, and then I can use direct substitution to get negative 1/9. So f prime of 3 equals negative 1/9. If you haven't already, go ahead and set up using the alternate definition for number 4. So here we go. F prime of negative 3 equals the limit as x approaches negative 3 of x plus 3 to the 1/3 power minus, this is going to all become 0. I'm hoping you can see this. Negative 3 plus 3 to the 1/3. That whole thing is going to become 0. All over x minus negative 3, which is just x plus 3. So now we have the limit as x approaches negative 3 of x plus 3 to the power of 1/3 over x plus 3. So we're going to use a little bit of algebra here. These, I'm going to put a 1 here for the to the power of 1. These exponential pieces here have the same base. The base is x plus 3. And The way that we can write this as one combined piece here is by subtracting the exponents, 1/3 minus 1. So this is going to give me the limit as x approaches -3 of x plus 3 to the 1/3 minus 1, which is the limit as x approaches -3 of 1 over x plus 3 to the 2/3 power. Now this problem, I can't use direct substitution to plug -3 in because I'm going to get 0 in the denominator. That would give me a vertical tangent 1 over 0. What this means is I can't factor this anymore. There's no conjugate for what we're working through here. There's no special trig. That means that this limit does not exist. And it looks like the reason it doesn't exist is because we're going to have a vertical tangent happening at this point. But what we can say is f prime of -3 does not exist. The derivative could exist elsewhere. It just can't exist at this particular value. So let's recap what we covered in this section. We talked about how the verb for derivative is differentiation, or to differentiate, and a function is differentiable if the derivative exists at that point or over a particular interval, and that in order to be differentiable we also must have continuity. The function must be continuous at that particular value. We talked about the 3 reasons that the function might not be derivative at a particular value: a discontinuity, a sharp turn, or a vertical tangent, and we looked at some graphs and situations where that may be the case. We talked about how the left and right limits need to be the same in order for us to find these derivatives, and we're going to apply that in the next section a little bit further. And then lastly, we wrapped up by talking about what the alternate definition is and how to find the derivative at a particular value using the alternate definition for derivative. So make sure you write down any questions you have, and I look forward to supporting you on this. Thanks for listening.